We are going to move right along in our afternoon presentation. Coming up now, we have a panel discussion moderated by David Steffelbauer. David, I say go ahead and take it away.
Thank you very much, and thanks also to Andrea Cominola and Riccardo Taormino for these nice pieces of art. I unfortunately don't have any art to share with you, but I think it will be a very interesting panel discussion. So I have very nice panelists for you that share a lot of thoughts about AI and hydroinformatics with you. So, as mentioned before, my name is David Steffelbauer, or David Steffelbauer in German. I'm a physicist by training, but I'm now the group leader of hydroinformatics at KWB, which is the Competence Center for Water here in Berlin. And this session is about hydroinformatics. So what the name of my group is also about. Hydroinformatics and new data sources. So we heard today a lot about new tools. So I also want to talk about new data sources, which then inspire new tools as well. So coming straight to the three excellent panelists that we have here and that I want to introduce to you now. Each of them has a very short presentation so that you can also see what their profession is all about. I would say ladies first. So let's start with Ina Vertommen. Ina Vertommen is an environmental engineer by training, and she is my counterpart in the Netherlands. She is the group leader of hydroinformatics at KWR. As you can see, there's a lot of confusion about KWB, KWR. KWB is Competence Center for Water in Berlin. KWR is even better. It's the Koninklijke Water Research Cycle Institute. So it's the Royal Research Institute for Water in the Netherlands. And so I would say, Ina, the floor is yours.
Okay, thank you for the introduction, David. I'll share my screen now. Well, thanks for the introduction, David, again. And well, you already told a lot about me. Let me just add that my background, or at least in the last years, I focused mainly on water demand modeling and network modeling and applying numerical optimization techniques to solve all sorts of problems related to water distribution networks. And okay, I will just keep talking. And maybe we'll have to do without the images. Okay, so I want to tell you first a little bit about KWR. It's the Water Research Institute in the Netherlands, and our shareholders are 10 Dutch water utilities, and we have one Belgian water utility on board as well. Most of our employees are researchers, and our motto is bridging science to practice. So we see it as our mission to translate scientific knowledge into applicable and practical solutions for the water sector. We, of course, also do international work, for instance, in European projects or other collaborations with universities, institutes, or water utilities. We have many expertises within KWR, and one of these is hydroinformatics. And we actually see hydroinformatics as the bridge between, on the one side, the challenges that the water sector is facing that were already mentioned today in the first keynotes. And on the other side, several technological and scientific developments that can be valuable to address these challenges. So we see it a bit as our role to support the water sector to prepare for an uncertain future by identifying and developing digital technologies and solutions for the sector. And we do that by focusing on three interconnected building blocks, which are research on hydroinformatics, data management, and software development. And examples of what we do are, for instance, risk-based decision-making, and that includes modeling and optimization or uncertainty, applications of machine and deep learning in the water sector, digital twins, just to name a few. And I want to talk to you a little bit more about one example of a very cool project we've been working on, which is the use of machine and deep learning for the identification of microplastics. And I think it comes as no surprise if I tell you that we use a lot of plastic. And unfortunately, that also means that plastic ends up in our water. And that is worrying because we don't really know what the effects can be on the environment and on our health. So it's important to monitor these plastics in our water. And that starts with analyzing water samples. And for instance, at KWR, we use laser direct infrared spectroscopy to get the spectra of different compounds in a water sample. And then the question is, when we get all of these spectra, we need to identify the plastics in question from this data. And this is a step that is usually done manually. So you imagine a researcher in a lab that is looking at each spectrum one by one and trying to compare it with references in a database and then identify from which polymer it comes. Well, you can already imagine what the problems of this are. First of all, it's a manual step, so it requires a lot of time from researchers. And on the other hand, the database with reference spectra are generally collected from unaffected polymers, so the really pristine ones. But the particles we detect in environmental samples, well, they've undergone extensive weathering due to the environmental conditions to which they were exposed. So the comparison is quite tricky. So we thought, can we do something to help researchers in the lab when doing that? And this is where AI comes in. So we've developed a first approach where we use machine learning to identify in an automatic manner different microplastics from their spectra. And we got an accuracy of almost 90% on that. Of course, these are good results, but as a researcher, we're never happy, right? So we wanted to improve this even more. So now we've come up with an alternative method that allows us to do the same, but with an accuracy of 99%. And the next steps in this project are to finalize all of this knowledge and put it into an application, so it makes it easy for this knowledge to be used by different colleagues in the water sector, also colleagues that don't have expertise with machine and deep learning or programming skills. And of course, to apply the same methods to other particles. We're already doing it with salt ions and it's working very well. So that's positive news. And that's it. I'm sorry you missed the slides. I had really cool images, but that's for next time.
Thank you very much, Ina. I can confirm that the slides were amazing. They really looked nice. So it's a pity for the audience that they were not able to see them. We in the Teams channel were able to see them. So they're really excellent slides. Okay, so coming to the next speaker, the second speaker that we have here in the panel is Antonio Moreno-Rodenas. And he is a civil engineer or hydraulic engineer by training, and he's at the moment the coordinator of the data science program at Deltares in the Netherlands. He has done a lot of machine learning and AI in the past for different applications, being a tracker for fat, grease, and oil in the sewer system, so also protecting the Dutch coast from being flooded, for example. But also privately, his guinea pigs are actually like benefiting from his AI skills. If he goes on holiday, he also developed an automatic feeding algorithm for them. So please, Antonia, I'm curious what you have to say.
Hi, David. Thank you for the very nice introduction. Okay, well, so as David said, I'm Antonio Moreno. I will try to do this presentation of my institution and the work that we do. And I'm lucky enough to have images, although Ina did it very well without them. But, well, I come from Deltares. Deltares is, I cannot change my... Yes, Deltares is a research institute that is also based in the Netherlands. It's kind of similar to KWR, but we focus in general water processes and subsoil processes across many different scales. We are basically a non-profit organization with 850 employees. Most of them are researchers. Let's say we have very, very specialized people in many different domains of expertise across all sorts of processes regarding water quality, water quantity dynamics in inland waters, coastal dynamics, and subsoil processes. We are based in, we are shared between Delft and Utrecht, and we basically are a knowledge institute. So we mix in-house knowledge about processes, so expertise, with experimental facilities, high-end experimental facilities that support our research. And at the same time, we have, or we collaborate with institutions across all Europe and all world, and we do general consultancy work on very highly specialized or weird problems, as I like to call it, across the world. And it's a very, very exciting place to work. But I prepare a quite fast presentation about some work that we have been doing on integrating machine learning or deep learning in particular to acquire new data sources in the water world in order to support our operations. And I think there is a critical concept that machine learning allowed in the last few years, that is bridging the gap between going from the lab to the field with optical observations. And that's quite relevant because when we are in a laboratory condition, we can control all sorts of environmental lighting. We can control, we have a very small envelope of conditions that they can appear in your experiment. So let's say it's easy for me or for some of my colleagues to develop a classical computer vision algorithm that will extract the features that we are looking for. So filtering by color, shape, motion, some sort of properties that we can describe kind of semantically or by code. Whereas when you go to the field, here you have some examples of sewer systems where you have cameras that they get dirty. You have all sorts of things that you would not expect to see in a sewer system appearing in your images. Or when you go to the field, you have to deal with a lot of environmental changes, from lighting conditions to rainfall that blocks your optical view, to the presence of a lot of processes that you were not expecting before, like a fish jumping or a bird passing by or a ship passing by. And these things you have to deal with. Fortunately, with this, let's say, deep learning algorithm, we can encode all these processes in a complete data set, hopefully. So we train, we generate data sets in order to train our model, and we hopefully try to capture all sorts of possibilities in the experimental envelope that we will see in the field. And then we train different routines in order to detect processes or measure things that you could do manually with a person, but these tasks become very intense, so they become very challenging for a person to, let's say, analyze these data sets manually. So we have an example where we have been working for the last few years, which is on the monitoring of the accumulation of fats, oils, and grease in sewer pumping stations. People and well, everybody disposes their oils in the sewer system. This undergoes chemical reactions inside the sewer that they become like hard soap surfaces, and they mix with all sorts of things that are down there, like plastics, textiles, and all sorts of things, and they form very thick layers that they cause clogging of pumping stations, damage to infrastructure, and in the end, flooding of streets. So these processes are normally still relatively unknown because there is no data sets describing them because it's very expensive or it's very challenging to have someone to go and check every time. So we develop a set of routines, let's say, computer vision system that you will deploy some cameras and they will automatically identify the motion of these dynamics. And we are conducting research in order to link these dynamics of fog in order to come out with the strategies to mitigate the accumulation and to increase the transportability of these layers. This kind of approaches, like this deep learning assistance for optical measurement processes, allow us also to bridge the gap between scales, so very large scales observed by satellites where we can process certain features, at the same time that we link it with ground-based monitoring from cameras or from other types of observations. This is a particular case from the monitoring of transport of floating vegetation and the clogging of intakes of power plants, where we try to acquire these non-conventional data sources from optical and satellite imagery to investigate the scales behind the transportability. And we do this also linking with conventional hydrodynamic simulators in order to do early warning schemes for these kind of things. These kind of machine learning approaches also allow us to leverage information in a much more intensively scale, at planetary scale, for instance, on the monitoring of hydraulic infrastructure. We have a very large project called the Global Water Watch, in which we try to derive or process global scale reservoir data sets and give it to the public for checking and for better informing their decisions. And just to finish, I identified some challenges that we'll discuss later. And the main challenges that I see, and well, they have been named several times by our colleagues before in the morning and now in the afternoon. The machine learning algorithms are still, it's challenged to develop them in a robust manner. They are subjected to the data set that you supply them. So if you supply the wrong data set, they will learn the wrong processes. And it's challenging to convince someone that you're using these algorithms in order to do an early warning scheme for a critical infrastructure if you cannot guarantee that at a certain point a ship is going to pass by and your algorithm is going to say, you have a huge mass of vegetation because you never allowed the algorithm to learn what a ship is. There is a problem also between the interpretability and the physics of the problem. And there is a big thing that I will hopefully discuss later, and is the fact that systems change, and they change fast. So if you rely purely in data-driven approaches, you have the risk of learning the past, but not the present. And that's one of the major challenges. Then all of this goes together with adoption in practice. So is this thing that we are doing just smoke, or it is useful at the end of the day for utilities and practitioners? And just to finish, we have a European project called Coyote Labs in order to allow the community to test new monitoring solutions in experimental facilities around the European Union, where we deal with this kind of smart sensing strategies for urban drainage. That's my part, David.
Yep. Thank you very much, Antonio. Also for throwing up already like some questions or some things that we can discuss at the end. But I want to give also the chance for our final member here to give a short presentation what he is doing. His name is Marten Hutten, and he is a data scientist at a water utility. So he's living the dream. We as researchers, we always have like a hard time to get data from water utilities. He's rightly there sitting at the source, and he can at the holy grail of data, and he can just like play around with the data that is there. So very, very happy to welcome you, Marten, here. So please, the floor is yours.
Thank you, David, for that warm welcome. Yes, we are sitting in a pile of gold, like Smaug in The Lord of the Rings, but unfortunately, it's not only gold, it's also silver, and sometimes it's just scrap metal. So let me share my screen, and I can tell you a little bit about my utility and where we are at the moment. So just to check that you can see my screen at the moment. It's shared on the main feed as well. All right, thank you. So I am a data scientist at Vitens. We are the largest water utility of the Netherlands. We provide drinking water to almost 6 million customers, which is about 1/3 of the Netherlands. We are a growing organization, despite everything. We have about approximately 1,400 employees, and we deliver 367 million cubic meters of water at a rate of approximately €1 per cubic to all our customers. We have quite a high customer satisfaction rate of an 8.3, and I think a relatively low non-revenue water percentage of around 6%. And what I also want to tell about Vitens is that I feel we are very much a utility which is undergoing the transition to a more digitized approach from a very traditional approach, mainly because we are having difficulties to find the right people to take over the work of others who are maybe retiring. It's starting to become more and more difficult to find new employees, and so we really need to find a way to capture the knowledge and the experts level the expert level knowledge that these people have, and try to put them into systems. So our data science team consists of 4 people, and we are basically split into 4 quadrants of disciplines. One of them is asset management. You can think about predictive maintenance models. Another one is customer data and smart metering. We have one test area in the north of the Netherlands, in which we have installed smart water meters in about 1,400 households, and we are really exploring the possibilities of this and what it can tell us about the water usage in our network, but also what it can tell us about our customers and how we can incentivize customers to maybe reduce their water usage. Besides that, we also have our own laboratory, which you can imagine processes large quantities of water quality data on a daily basis. So this is really a treasure trove for us as well, to find what is going on in the network, and also to find new, maybe like Ina said, maybe plastics or other substances in our water, and we can make decisions based on that. And a relatively new one is also energy management. Of course, this is becoming a bit of a very hot topic in society at the moment. And we want to see if we can, well, first of all, decrease our energy usage, but also if we can maybe adapt our cleaning and distribution of water to match more the availability of wind and solar power. So my work at the moment is located approximately here. We switch our topics quite oftenly, but right now I'm working on this last topic. So one thing that I would like maybe to discuss today is what we notice from a data science perspective within a water utility, is that we have this amazing tool, this great hammer, this machine learning and AI models, but how can we incentivize others within our company to ask the right questions? I think this is one of the interesting things we could maybe discuss today.
Thank you very much.
Sharing.
Thank you very much, Marten, for this nice introduction, and also to giving us an overview of your work, and also about that you want to discuss this problem about, like, if you have a very powerful hammer, then suddenly every problem becomes a nail. So
yeah, exactly.
That's the viewpoint then. Nevertheless, I wanted to start with something a little bit like easier, or going like into the direction of the topic of this talk, which is or this panel discussion, which is new data sources that I wanted to discuss at the beginning. And therefore, we have seen like a lot of different data sources that are available. Ina showed, for example, laser spectrometry, how this can be used for the water cycle. Antonio, some pictures about using video cameras with convolutional neural networks. Marten, you are also working like with a lot of data there. So I just wanted to ask, because there's something very interesting. Ina, I know that your group in Hydroinformatics has done something on text mining and natural language processing in the past as well. So using written complaints from that came to water utilities. What do you think, like with the words of Antonio? Is this smoke, or is it useful? What's done there, or is it metal or gold? So do you think there's a future in that?
I think there is definitely a future, but I actually, what Marten just said, how to convince people to use it is challenging. So Well, the research that you're asking about was actually done together with this one about microplastics. So we were just trying to see what the added value of machine and deep learning in general could be for the water sector, and we just picked out 2 examples: the microplastics one, and the customer complaints. And I think because microplastics is a bit more related to health, it's gained a bit of more of attention, and it's just easier to sell. It's like a hot topic, and the customer complaints is quite difficult. When we present it to water utilities, they are very enthusiastic, but then it's difficult to take a next step. But what we did was use what we see is that, for instance, in the Netherlands, the water utilities register these complaints in different manners. So the first challenge is to, well, combine different formats of data and levels of details in data. But once you have done that, it's not very difficult to train an algorithm to automatically extract the right information out of a message. But then the question is, what can you do with it? I think it helps the customer complaints departments to deal with these type of messages in a more efficient manner. But yeah, key is implementation, and we didn't find a solution for that as well. I think it's not gold, but maybe silver. But it's just not so. It's not just such a sexy topic as microplastics, I'm afraid. But I'm curious to hear how Marten thinks about this, because of course he comes from a water utility.
Yeah, would love to respond. Yeah, what I think is this is a very promising machine learning method, of course. But also it's quite far detached from our core business, which is making water and distributing water. And this means that I think that the impact that this technique can have is well, relatively limited. I think we have also done some exploratory work to see if it's possible to train a chatbot to interact with our customers to answer the more basic questions, which was relatively successful. But at the moment, it's not at the level where we can fully implement this. So I think there's some benefits, but regarding drinking water, it's quite far detached from the core business, so hard to get traction.
Thank you very much, Martin. I also wanted just to stick with you to answer me another question.
Mm-hmm.
I had a very, very interesting discussion once with one of your co-workers, with Mario, I think is his name, who said something that you're sitting on this pile of data, and he feels a little bit, he's got like this dream job, so he feels a little bit like Sherlock Holmes trying to find something useful in this big pile of data. So according to that, what data that you thought is like first looked like metal, but turned out to be actually pure gold in hindsight? Is there a good example for that?
Yeah, one thing that comes to mind is I did a project on determining the state of our clean water reservoirs, and at first sight, it looked like there was not much that we could determine. So we know the water quality going in, we know the water quality of the reservoir, and basically we wanted to know, can we say when we want to when we need to clean our reservoirs, which is of course it's a costly thing to do, and you have to take the reservoir out of commission for a short period of time. And it first seemed like there were no explaining factors. But then when we dig through the actual cleaning moments of every reservoir, we could see that there was in fact some correlation between the water quality and the cleaning. We were just looking at it from the wrong direction. So yeah, this is one of the things that I didn't expect, that just the order number of we've cleaned this reservoir, which is basically almost unstructured data, was so significant in the end.
Well, that's quite interesting. I think also to look at the data like from causality perspective from a different way. Another question for Antonio. So we heard today also a keynote about using this flood forecasting algorithms, artificial neural networks for that, also with video data, with satellite data, and the note that you worked also a lot on that. Do you think that those models that we have now, those tools, those hammers, as Martin said it, are they changing completely our way of how we are going like to perform like hydraulic engineering in the future?
I hope not, David. I mean, it's a very, very interesting question indeed. I don't see machine learning to be the replacement of physically based knowledge, and I think we shouldn't consider that. It should be a tool to enhance our capabilities. But I am a little bit wary always of purely data-driven algorithms. They can work well in certain conditions. They can fit well to your training data set, and especially in large-scale processes, they might work well. But when you are dealing with urban flooding, I mean, you know David quite well also. Processes are very dependent on very small things, like you have a pipe that is clogged. You have and it's very difficult to capture this from a purely data-driven perspective from past data. So I think we shouldn't go into the world of okay, we are at a changing moment in which now everything is going to be data-driven, everything is going to be machine learning powered, but it's more like, or as I see, as a very, very powerful complement for us. We can, I mean, when we are dealing with uncertainty analysis or we are dealing with control systems, you have normally a physically based model, which is the best representation of your knowledge. But normally these models are quite heavy, quite slow, and you cannot build them. I mean, you cannot operate them as you would like to draw hundreds of thousands of samples to do parametric calibration or to do error analysis, etc. There are a lot of techniques in machine learning to accelerate these models without disrupting the physics behind it. And I think that's very powerful. It's also very, very interesting to what they were presenting at the beginning, and I don't take any value from it, absolutely. But I don't think we will or we should drop our approach of understanding the physics from the first point.
I see also a lot of head nodding, and as well as like I'm a physicist, so I can just agree with that what you just said. There's also Antonio, I know that you worked, like you did your PhD in a project which was a Marie Curie PhD that you did, and the project was quantifying uncertainty in integrated catchment studies. So being like in this urban environment, putting all this uncertainty together, and I can imagine that it gets a lot messy. Do you have like any trust then in the models at the end then when you feed them with all this messy data in the beginning?
Yeah, I think the conclusion of my PhD is that, well, and not only my PhD, a lot of people, is that all models are a lie and some of them are useful. It's very challenging to model these very complex processes, indeed. But through, I mean, the most important thing is data. And I think Oliver at the beginning of the session mentioned it, and I fully agree with it. Is data and data of quality. Then from that, you use your knowledge, you use all the tools available to you in order to understand the processes behind your system. And from that, you draw conclusions and then you create actions. But I think one of the conclusions of my research, like I spent 4 years working in a catchment in the south of the Netherlands. It was a river and city integrated catchment system. And I spent 4 years investigating how the uncertainties propagate. I had very nice conclusions. Okay, this part of the system is more important than this other one. By the end of the 4 years, the system has changed. There are new investments done in the wastewater treatment plant. The whole control system is completely overrun and changed and improved and so on. So that's the risk. Like, systems evolve, and how do you keep with this evolution? I think that's critical. And I don't think we are yet to a point where we have generalized sufficiently our AI models. There might be a time where we reach there. But that's one of the challenges that we have to bridge, probably.
Very interesting. So your PhD ended with all models right, but some are useful. Mine ended with to summarize the summary of the summary. People are the problem. So it's also about the uncertainties that people introduce in the systems, but it's that we can't model. And on the other hand, it's also about like the decisions that are taken from the data that is there. So I'm also a little bit curious for maybe the question for Ina. So if all those models are uncertain and all this data is uncertain, so how can you convince decision makers that actually what your AI model is showing you, or what your model is showing you, is actually like a good decision?
That's a big challenge, right? I mean, I heard a lot of interesting things now, and I was indeed nodding because I agree with everything you're saying. Well, thinking about uncertainty and how to communicate that and how to make decisions is, well, what at KWR, what I love to do and a lot of my colleagues really love to do, but it's such a big challenge. And I believe there's a lot of knowledge and experience in the scientific community at the moment about this. We have so many metrics and approaches. I mean, just think about all the definitions that we can come up with for robustness and reliability and resilience and deep uncertainty and scenario-based approaches. We have that all. We have increasing computational capacity. So it's getting easier every day to take uncertainty into consideration when modeling. So we have many ingredients to take this step to move from deterministic to risk-based decision-making. But application in real life and in industry is a big challenge. And I think on the one hand, it's very difficult to communicate about it. I also don't know the solution. So I would love to hear everyone on, well, if you have tips on this. And it doesn't always fit a standard approach that is used in the industry. So for instance, when you design a water distribution network and you have to make decisions, this is often done by trial and error and by hand. This is the practice by most water utilities. And the deterministic problem is already so complex that if you add uncertainty to it, it's completely unfeasible to solve it. So to take uncertainty into consideration, first, we need to change the way you address this problem, for instance, by using numerical optimization or making some of these steps automatic. And only then, when this is embedded, then you can start adding uncertainty to it. So I think we need to make little steps and try to not make it a black box, but try to communicate uncertainty in a clear way, saying the answer is not this, it is this with a specific reliability around it. In 90% of the cases, this will work well, and try to shift this way of thinking and to communicate. But it's a big challenge.
Yeah, so let's forward this to somebody from the industry. So Marten, you're sitting there in the industry, so directly at the water utility. How do you convince them that your hammer, let's switch to the Marvel universe, so it's like Mjolnir, like the mighty hammer of Thor, is like the really best one, and that you can solve these problems also with all the uncertainties there?
It's a big challenge. Of course, communication about your results is one of sometimes for us who are more into the data side of things. It's a difficult part of our job, but I think sometimes it's also about knowing what to and what not to communicate. If you present a good solution in which you have faith and you know that it is it's good, then presenting it with too many uncertainties can sometimes undermine the point that you are trying to make, while there's definitely benefits to your solution. So I think it's very important to know your audience, of course, and to really focus on the power of your solution. And I think that's one way to move towards implementation, which is always the most difficult part.
Very interesting. So what I heard like in the first keynote, I think, is like data lies or data can lie. Then it's also the models lie, according to Antonio. Then also data scientists in my company are telling like the half truth to be able.
It's never the half truth, but it is. Of course, you can determine which part of the project you want to highlight and which not. But it's always a choice.
Yeah. But the big question is also how can we increase the trust in actually like the models, in the data, in and so on. So that's, I think, also Antonio gave like a good comment on that, which is actually we can't do this without the physics behind it. That everybody could agree. So maybe it's not about like using machine learning in a dumb way, like without like prior knowledge that we put into it, be it numerical equations, be it mathematics, be it physics, and that can make like our tools more powerful, so that the utilities really have a benefit from it. Yeah. I wanted just to ask a last question, a very short, and I'm really hoping to get like very short, quick answers from you, maybe one sentence or something like that. And because we have here a completely like Dutch panel discussion, excluding me, so if we're talking about AI and machine learning, we are always like looking to Silicon Valley and these companies. If we're looking about water and hydroinformatics, the focus shifts suddenly, and we are in the Netherlands. So why do you think are the Netherlands at the forefront? This tiny country, not a comparable country like Austria, my home country, for example. So.
Yeah, that's a very curious question. I was not expecting, David, and I'm not Dutch originally, so that's I have other perspectives, let's say. But I will say there is a very good, let's say, good connection between the industry and the research world in the Netherlands. When I first came here to do my PhD, I remember there was this kennisprogramma, what they call it. The whole industry of urban drainage will around the Netherlands will collect, let's say, a budget, and then they will push it to fund PhD research. And I found that to be quite impressive. Like that was not the idea that they had of the urban drainage industry. So I guess that's a very, very, there is a good push from the industry in order to innovate and to keep in the forefront of the state of the art on techniques. And at some point, this is shown to have a feedback loop towards the industry back.
Interesting. Marten, from the industry, what are your thoughts? Very, very quick, very short.
Well, I think traditionally the Netherlands has always been a country that's very focused on water. So maybe this is just something that that we had a little bit of a head start on. So yeah.
And Ina, your quick thoughts on that?
Well, actually, I'm also not Dutch. So I bring a bit with my history from Portugal with me to answer this question. When I started working at KWR, I heard a lot of times a bit as a complaint that the water sector is very conservative and it's very difficult to make changes. But coming from abroad, I see the Dutch water sector actually to be very proactive compared to others and other countries. So I think that really puts us in the forefront. So the Dutch water utilities, they want to do more with data, want to do more with knowledge, for instance, to replace a pipe before it breaks. And this is not the case in other countries where you just wait for the water to, be on the street and then you go and look for a leak. So I think it's this proactiveness that's actually really important and really motivating.
Yeah. So with this remarks, I think I will close the session. I see also that we are also running late. So thank you very much, Ina. Thank you very much, Antonio. Thank you very much, Martin, for participating in the session. It was a pleasure discussing with you this hydroinformatics topics.
Thank you, David.
Bye.
And a great big thanks from me too. What an exciting panel. And I thanks so much for your final thoughts there, panelists, especially the Dutch being proactive. It was quite lovely to hear. Thank you so much for your contributions today.